Assalamualaikum and hi everyone. We are from Group 10. We'll be presenting about
Experiment 16.
which is a flow bench for our webinar and Viva task. So first of all, I will introduce my group members in this group, which is Oh Hon Kiat, Suvitra, me and myself, Kuat, and also Tan Wee Hui. Each one of us will present each part, which is I'm gonna present the introduction, objective and theory part, while Wee Hui will present about the procedure of this experiment. Oh Hon Kiat will present about the result and discussion, while Suvitra will present error analysis and conclusion. So, without any further ado, I will discuss about the introduction first. So, in this experiment, we will conduct 4 different sub-experiments, which are experiment A, experiment B, experiment C, and experiment D. The apparatus that we will use in this experiment are manometer, venturi, orifice, pitot test tube, and pitot tube with adjustable scales. In experiment A, we will measure the difference in pressure by using an inclined manometer with different height of damper, while in experiment B, we will measure the difference pressure using orifice plate and venturi nozzle, and experiment C, we have to confirm the Bernoulli theorem, which is related with the relationship of the static pressure, total pressure, and velocity head. While in experiment D, we will calculate the difference in pressure at certain position, in certain length, and to make sure it is a turbulent or laminar flow. Like I said before, we will conduct 4 experiments, which is experiment A for the determination of centrifugal air blower characteristic, experiment B, flow metering devices, experiment C, Bernoulli principles observation for air, experiment D, investigation of the development of fully turbulent flow within a pipe. Next, I will go to the objective of this experiment. For experiment A, the objective is to learn the centrifugal air blower characteristic through the plot of static pressure rise across the blower against the volumetric airflow rate. While for experiment B, we will discuss about the flow measurement of air using 3 different types of flow metering, which is orifice, venturi, and pitot static tube. In experiment C, it is conducted to determine the conservation of energy taking place in the Bernoulli apparatus to confirm the Bernoulli theorem, while last but not least, experiment D, to investigate the development of fully turbulent airflow within a pipe. So now I will discuss more on the theory for experiment A first. For experiment A, we need to calculate several terms in order to fulfill the objective of this experiment, which to learn the characteristic of centrifugal air blower through static pressure rise across the blower. First, we need to calculate the volumetric airflow rate as shown in the slide to get the average air velocity. Then, we need to calculate dynamic pressure in order to get the static pressure rise as shown in the slide on the number 4. For experiment B, we will use 3 different types of flow metering, which is pitot static tube, orifice plate, and venturi nozzle. In all these types of flow metering, we need to determine the flow rate first in order to get the pressure difference. For the pitot static tube, to determine the datum point, it should be pushed into the duct, but until only touch the sidewall. The formula is shown in the slide. So for the orifice plate, the formula for volumetric flow rate is as shown in the slide, which is Q equals to C naught A naught Y over square root of 1 minus D naught over DI bracket power of 4. But the uncertainty value of coefficient must be plus minus 1.5% only. For the venturi nozzles, the formula provided for the volumetric flow rate is equals to QV equals to CV AV Y over square root of 1 minus bracket dV over DI bracket power of 4. Next, for experiment C, we will test the Bernoulli theorem in order to determine the energy, but there is several cases that need to be considered, which is at the steady state condition and single streamline, horizontal ductwork, and for gas flow. This is as shown in the slide. All those three conditions will have different types of formula in order to get the pressure difference. For formula for gas flow, it is as shown as the slide, which is P plus rho U squared over 2G equals to constant. But the procedure of the experiment will be explained in detail by Wei Hui in the procedure part. Last but not least, for experiment D, we need to investigate the turbulent airflow properties inside a pipe. As we know, the Reynolds number for turbulence is 4,000 and above, and if the Reynolds number is above 4,000, the flow will be considered as a turbulent flow. In this experiment, we will have 15 different positions, and from that, we need to measure their pressure difference and volumetric flow rates. And this will be also discussed in details by Wei Hui in the procedure part. But here we have three different static pressure, which is static pressure drop along the pipe, static pressure rise at a pipe expansion, static pressure drop at pipe inlet. The formula for static pressure drop as shown in the slides, and for static pressure drop at inlet pipe, it has two cases, which is separation occur in streamline and the opposite of that. For the first case, it has two formulas to calculate pressure drop, while for the second case, which is the opposite of the first case, which is only have one formula, which is delta P equals to K rho V squared over 2. For the static pressure drop along the pipe, it only have one formula for static pressure drop, which is delta PF equals to 4 FL rho V squared over 2D, and the F value for in the static pressure drop formula is as a friction factor, and the friction factor formula is equals to 0.5 d2 multiplied by delta PF equals to rho LV squared. For the static pressure rise at the pipe expansion, the formula for energy that causes by frictional force is equals as delta F equals to VI squared over 2 modulus 1 minus D1 over D2 close bracket modulus power of 2. And this part will finish for the theory in all the experiment that I explained before. So to continue the discussion of this experiment, I will pass this part into Wei Hui to explain the procedure of the experiment A, experiment B, experiment D, and experiment C.
Next, let us have a look on the procedure. There are 4 experiments included in this airflow bench experiment. For the experiment A, determination of centrifugal air blower characteristics. For the first step, set up the assembly as shown in the figure 1 below. Then, step 2, connect the inlet static pressure point PT3 to the limb of long manometer of P010 dual manometer. Step 3, connect the outlet static pressure point PT4 to the reservoir of long manometer of P010 dual manometer. Step 4, connect the inlet mouth pressure point PT2 to the limb of short manometer P010 dual manometer. Step 5, Level and zero the P010 dual manometer with both manometers in the upright position. Step 6. Set the height of P006 damper to about 10 mm above of P005 damper holder. Step 7. Switch on the P001 blower. Then record the reading of long manometer and short manometer. Then record the inlet air temperature with a suitable thermometer or temperature sensor. Step 10. Increase the height of P006 damper in 5 mm interval until the height is 70 mm above the end of P005 damper holder. Step 11. Record the manometer reading at each setting. Next, let us proceed to Experiment B, flow metering devices. Step 1. Set up the assembly to include components as outlined in Figure 2 below. Next, a wheel of equipment setup is shown in Figure 3 below. Step 2. Push the P012A orifice 65 mm plate into P012 inlet adapter housing. The orifice plate is positioned with the countersunk side downstream from the inlet. Note that the engraved label should face upstream. Step 3. Adjust P013 stand to a suitable height to support the overhanging section of the assembly. Step 4. Fit P014 Python static tube 1 assembly into the 1 meter ductwork at any of 3 radial positions, PR1, PR2 or PR3 with the nose facing upstream air. Next, plug off the other 2 radial positions. Step 5. Connect P104 Python static tube to the long manometer of P010 with the tube top, which is total pressure, connected to the reservoir, and tube side static pressure connect to the limb. Then connect the pressure tapping PT1 of P012 flow metering device housing to the reservoir of small manometer of P010 dual incline manometer. Step 7. Connect the pressure tapping PT2 of P012 flow metering device housing to the limb of small manometer of P010 dual incline manometer. A schematic diagram is shown below. For Experiment C, Bernoulli Principle Observation for air, the first step, set up the assembly to include components as outlined in previous Figure 2. A typical assembly is shown in Figure 4 below. Step 2. Push the P021 Python tube to maximum insertion. Step 3. Connect the P021 Python static tube to P012 dual manometer as indicated below, which is the top total pressure must connected to the reservoir of long manometer, while the side, which is static pressure, must connected to the reservoir of long manometer. Step 4. Position both manometers in top incline position, level and zero both. Step 5. Set P006 damper to half open. Step 6. Start P001 blower, then adjust the height of P006 damper until long manometer reading is about 0.6 kPa. Step 7. Position the P021 Python static tube so that its static pressure holes are aligned to 210 mm position. Then record the reading of long, which is total pressure, and short, which is static pressure of manometer. Step 9. Repeat the step above with P021 Python static tube move in 10 mm increment towards the ductwork end until the static pressure holes of P021 tube are aligned to 0 mark on the scale. There are several notes for Experiment C. The first one, whenever a manometer displays negative pressure, pull out the tube connection from the manometer reservoir, then reconnect the tube to the manometer limb and record the pressure as negative. The second one, whenever a manometer reading gets too close to maximum scale of top incline position, reposition the manometer to higher inclination, then turn off P001 blower and re-zero manometer and restart the blower. The third one, scale multiplier must be incorporated into the reading depending upon the inclination according to the table provided on P010 dual manometer. For the last experiment, experiment D, investigation of the development of fully turbulent flow within a pipe. Set up the assembly to include components as outlined in previous figure 2. Then a view of arrangement is shown in figure 5 below. Step 2. Fit P014 pitot static tube 1 at the PF4 position. Subsequently, connect the tube side and the tube top tapping to the limb end of the long manometer respectively at P010 dual manometer. Then set both long and short manometer to upright position and level and re-zero the long manometer. Step 5. Plug other alternative static measuring PF3, PF2 and PF1. Next, let us have a look on determination of volumetric airflow rate using pitot static tube. First of all, set P006 damper height 20 mm above the P005 damper holder. Then start P001 blower. Transverse P014 pitot tube at positions across the pipe according to figure 6. Next, record the manometer reading. Then fit the pitot tube at other positions, which is PF17, PF18, PF19, and repeat the step above. For another procedure, the first step is, while the P001 blower is still running from the previous experiment, connect the limb of the short manometer in upright position to PF1. Then record the reading of long manometer, then repeat this at other positions. Note that section A and section B may be repeated at different airflow rates by adjusting height of P006 damper.
I am Oh Hong Kiet and I will present results and discussions. For experiment A, the height of the damper is manipulated to obtain a different flow rate in order to get the results. After that, the differential pressure is calculated by using static pressure minus total pressure. The differential pressure is used to obtain the volumetric flow rate value by using equation A1. By using equation A2, air velocity is calculated in order to proceed with equation A3 to get Reynolds number. At the same time, equation A4 and A5 are used to get the static pressure rise across the blower. All these data are tabulated as shown. A graph of the static pressure rise across the blower versus the volumetric air flow rate is plotted. The graph will be shown later. In experiment B, the length of the pitot tube is manipulated with the increment of 10 mm at different positions, including from the top and the side with 4 types of testing apparatus. The initial procedures of calculations are almost the same as the previous one. After obtaining the corrected pressure differences, the effective differential pressure needs to be calculated with the formula of the square of average of the square roots of the 24 individual differential pressures. The mass flow rate and average velocity are calculated too. To be taken note that the alpha value in the equation to calculate mass flow rate needs to be referred. Then, both orifice plate and venturi nozzle have their own formula to calculate the volumetric flow rate. Next, the data and results are tabulated as shown. Now, I will show you the results from the top position. As you can see, this is P012A orifice 65 mm, P012B orifice 95 mm, P012C venturi 65 mm, and P012D venturi 95 mm. And then, this is the combined table of all 4 types of apparatus with effective differential pressure, mass flow rate, volumetric flow rate, average velocity, and Reynolds number. The same tabulation method is repeated for the repeated experiment from the site. This is the results. P012A orifice 65 mm, P012B orifice 95 mm, P012C venturi 65 mm, P012D venturi 95 mm. And the same thing, this is the combined table of all 4 types of apparatus with the results. In experiment C, the velocity head values are obtained by using total pressure to subtract the static pressure. Then, the results and data are tabulated as shown. We have the table of total pressure from the top connected to the reservoir of long manometer and static pressure from the side connected to the reservoir of the long manometer. In experiment D, the air velocity is calculated at each radial position by getting the volumetric flow rate as the previous equation discussed. Then, the value of inlet loss coefficient, friction loss due to sudden expansion, and fanning friction factor need to be calculated by using the graph shown in figure D4. Unfortunately, the equivalent roughness of long pipe is unable to be calculated as the data points are not in the range of the relative roughness. All the answers that are calculated are tabulated as usual. Next, I will explain the discussion part. A fundamental theory that needs to be known, the long manometer is used to measure total pressure, while the short manometer is used to measure static pressure. In graph of experiment A, which is the static pressure against volumetric air flow rate, the trend that can be seen is the higher flow rate, which is caused by the higher the damper open, the higher the total and static pressure. The error that might be happen in this experiment is parallax error during changing the damper height and also observing the reading. So, the way to minimize the error is to fix one person to observe the reading, and the same goes to the one who manipulated the damper height. In experiment B, the results of 4 types of venturi and orifice is compared, and the trend can be seen. In both venturi and orifice, the one with smaller diameter will obtain a larger pressure difference. If compared in terms of diameter, orifice has larger pressure difference than venturi. This can be explained as the smaller diameter, the fluid flows faster, and kinetic energy increases, then more pressure drops. The errors that might be happen are the airflow is not parallel to pitot tube, and the increment of length of pitot tube is not fixed originally. The ways to minimize the errors are to try to maintain the parallel of airflow and pitot tube and use pen correction fluid to mark the pitot tube respectively. That's all from my part. Discussion for part experiment 3 and 4 will be continued by Suvitra. Thank you.
In experiment C, we want to confirm the Bernoulli theorem. Bernoulli theorem is the relation among the pressure, velocity and elevation in a moving fluid in which the compressibility and viscosity are negligible. In other words, Bernoulli's theorem stated the increase of velocity of fluid causes the pressure drop. From the graph of corrected total pressure, corrected static pressure and velocity head against the duct position shows a negative total pressure, which fits the Bernoulli theorem that pressure must drop when there is a fluid flowing through with velocity. Moreover, while doing this experiment, there is a parallax error, which is the reading is not consistent due to energy loss when the air is flowing. This error caused the fluctuation to occur and we got the non-consistent data. Therefore, to minimize this error, we can take the reading twice or repeat the experiment and get the average value of result. In order to compare which one is more accurate or decreased the distance from the inlet source. Next, in the experiment D, we have to measure the static and the total pressure in 15 different positions in the pipe by using the manometer. The distance between the spots are measured because not all the positions has the same distance. During this experiment, the pipe is not connected well or not tight enough. This causes the leakage of air when it flowing in. So make sure all the pipe closure is connected tightly to avoid the air leakage from the pipe before starts the experiment. Furthermore, the error that might occur is when we want to connect the limb of the short manometer in the several positions, we are not fully fit the pitot tube. Thus, try to fit the connection as fit as possible. Now we will see the error analysis for this experiment. Throughout this experiment, we found that we have encountered some errors, which mostly the parallax error. This parallax error is due to different persons have different reading style that cause different value recorded while reading the pressure in the long and short manometer. Furthermore, sensitivity of apparatus used to measure certain data. Error occurs when we measure the damper's height using ruler where the scale are quite small, which we can't afford to avoid. Apart from that, we also found errors from human or environment. The reading can be changed if there's anything that blocks the blower, even to determine the datum point for the pitot tube. Static scale, the pitot static tube should be pushed into the duct until the head touches the side wall. There will be changes in the reading in case the push is too hard until bend the nose of the tube away from the wall. In conclusion, we have done our very best even though there were some errors occurred throughout this experiment which have been discussed earlier. We successfully achieved the objective of each experiment that we have conducted. There are 4 different kinds of experiments conducted in this laboratory session. The first experiment is determination of centrifugal air blower characteristic, which is to understand the characteristic through the blower against the polymetric airflow rate. When the damper height increases, the resistance of airflow decreases and the air moves faster. Therefore, the static pressure increases and the velocity also increases. This is only valid until a certain height of damper, because after one point the height of damper is no longer a limiting factor. Next, flow metering devices, which included piezostatic tube measurement, orifice plate and venturi nozzle. Python tube was plugged in the devices with different height from the most bottom of the tube to the top with 10 mm interval in between. The pressure drop in the duct can be minimized by using an orifice meter or venturi meter with a larger opening. Further pressure drop reduction can be achieved by using a venturi meter instead of orifice meter, as it can reduce loss due to sudden expansion. The results have recorded and compared in the data table. In this experiment, Bernoulli's theorem is verified. Decrease in velocity head is accompanied by an increase in pressure head and vice versa. The relationship between the Bernoulli theorem and the total pressure, both static pressure and velocity head, was stated clearly. In the Lux experiment, the air flowing through the duct is turbulent throughout the process. Expansion and contraction cause changes in the velocity through inverse proportion, as the principle of conservation of volume holds. The air is considered incompressible in this experiment as the pressure involved is low.
That's all from us. Thank you for watching.